them today. His thesis consists of non-parametric system identification modeling of neural spikes transformation using deep learning and applied machine learnings to guide closed-loop simulation for brain-computer interface for memory restoration. Thank you so much, Bryan, and we are looking for your talk. Thanks. And this, the title is Validation of the Convolutional Neural Network and Model for Spike Transformation using Generalized Functional Additive Models. Thank you so much.
Thank you very much, Dr. Farhoodi, for the warm introduction. And on behalf of myself and my advisor, Professor Dong Song, I want to thank everybody for taking the time to listen to our talk today with the title already introduced. So just a quick plug for a recent paper that I encourage you to look up if you find anything that I spoke about today interesting that was recently published in IEEE EMBC. In July, it's under a very similar name to the talk today, and you can find it right now in IEEE Explore if you have any interest. So we're interested in identifying the causal relationships in neural activity, and this is a very important problem in neuroscience and neuroengineering because successfully identifying these functions is necessary in order to understand how neurons transmit information between one another. So we know that neurons communicate with each other via spikes, with individual neurons receiving spike train inputs from multiple neurons while also sending spike train outputs to other neurons themselves. And any modeling approach of this activity has to account for the dependence of these output neuron spike trains on both current and past spiking activity of the input neurons. And it's also well known from many prior studies that these transformations consist of both linear functions and nonlinear functions, which we refer to here as kernels. So a lot of different modeling methods have tried to capture these kernels, including basic linear models, generalized linear models, generalized additive models, and generalized functional additive models. And I just want to quickly review the difference between them and their power, because this is how we generated our synthetic data. So a basic linear model is what we all learned in middle school, y equals mx plus b. We show it here in vector form. A generalized linear model expands on a basic linear model with relaxation of assumption of the normal distribution of error, and as well as providing a link function that can essentially allow for an arbitrary distribution in the outcome variable. And the best known example of this to most people is probably logistic regression. And then a generalized additive model expands on the generalized linear model by not modeling on the initial predictors themselves, but actually modeling on smooth functions of these predictors. And this is able to capture nonlinearity depending on the functions that you use to transform your initial predictors. And then lastly, a generalized functional additive model expands on the power of a generalized additive model by integrating the predictors with regression functions. And this can allow for even better ability to model nonlinearity in the system. So, as two of the previous presenters talked about some of the work from our lab, we've used a generalized functional additive model before, and this can expand these unknown input-output transfer functions with a set of basis functions, and this can facilitate model estimation by reducing the total number of model coefficients to be learned. And some of the past work in our lab has used a multi-input, multi-output model, which itself is a combination of multi-input, single-output models as shown here in the picture, in order to capture nonlinear dynamics. And although we found some success with this, the MIMO model itself is still a shallow model in comparison to some of the contemporary model architectures in deep learning. So I think the audience is probably very familiar that over the last 10 years or so, the convolutional neural networks have redefined state-of-the-art performance in image classification. And although a basic convolution layer itself is a linear system, you can introduce nonlinearity into the system in the form of nonlinear activation functions. And we hypothesize that a potential first step in capturing the nonlinearity in these neural spike transformations is to use a nonlinear activation function that's ubiquitous within CNNs these days, called the rectified linear unit activation. And we additionally thought that the depth of a convolutional network when compared to the MIMO model would enable it to better capture kind of complex, more sophisticated nonlinear dynamics. And then additionally, all these other properties of a CNN that we've all kind of come to know and love, parameter sharing, translational invariance, translational equivariance. We thought this might also help to be able to recover some of the nonlinearity in these systems as well. So in order to do this, we treat two-dimensional spatio-temporal patterns of spikes as binary images to try and recreate the success of CNNs in order to, model spike transformations. And this, becomes a binary classification problem using a CNN where our data is images that we obtain from input neurons over time, and our labels are a binary 0 versus 1 and an output neuron, representing whether there's absence or presence of a spike in that output neuron at a given time step. So in order to do this, we generated synthetic data in MATLAB using a generalized functional additive model, as I showed previously, in order to test the performance of a CNN to recover the probability of spiking in a single output neuron over time based on input from 16 input neurons. So we use recovery of the true model kernels that we use to generate the data process as a performance metric for the CNN model. And we developed 8 neurophysiologically inspired kernels, and these had different shapes and delays. The input signals were 16 IID Poisson processes with a 10 hertz mean firing. And to model these 16 neurons over about 40 minutes approximately at a 500 hertz sampling frequency, this ended up being a 1.2 million by 16 matrix for the input data. So here I just show the general form of a generalized functional additive model that we use to generate our ground truth in the output neuron. So we sum theta 0, which is representative of the mean firing rate in that output neuron, with each input neuron individually convolved with one of these neurophysiologically inspired kernel functions. So I just saw a single example here for input neuron 1 being convolved with the function on the left. And then we pass that sum to the inverse probit link function in order to map this to a range of 0 to 1, which is representative of the probability of spiking in the output neuron. So of the 16 input neurons, 8 were generated as shown here with these neurophysiologic kernel functions, and 8 were generated with kernel functions set to be zeros. And the 0th order kernel represented by theta naught there was set to negative 7.6 approximately, so that we could get around a 1 hertz baseline firing rate in the output neuron. So we wanted to do this so there was a high level of sparsity in the output neuron, so we could kind of see how robust the CNN was to extreme class imbalance that we would typically see in human spike sorted data. So this created a time series of probability at firing in the output neuron at time t. And the ground truth labels as spikes in the output neuron were then realized with the Bernoulli probability mass function with the probability equal to the firing probability intensity function. So this eventually yielded a binary 1.2 million by 1 array as our final model output. So we then took this input data and the output labels, and they were split just into standard 0.8, 0.1, 0.1 train validation test sets, and create the input neural time series images to actually train the CNN. We used a modification of TensorFlow's time series generator utility class, which created a sliding window, which is shown here, not to scale with our data, but just to give you kind of a picture of how we did this. So we used our modification of the time series generator to create this sliding window that created images of size 256 by 16, where 256 time steps from t current to t current minus 256 from the 16 input neurons were output with a binary label from the output neuron at time current. And then, subsequent images were created with the sliding window with a sampling rate of 1 and a stride of 1. So this created approximately 960,000 training images for the model. So we then developed a sequential model within Keras with a TensorFlow backend and performed manual architecture optimization with respect to the number of layers of convolution, the number of filters per layer, stride and filter side within each layer as well. And we also performed some manual optimization in terms of the proportion of dropout within a Keras dropout layer that we included and used, as previously mentioned, the rectifier linear unit activation of all the layers of convolution. So all models that we tried were compiled with a sparse categorical cross entropy with an atom optimizer and default hyperparameters. And our best performing model is shown here, which consisted of 5 convolution layers, a flattened layer, dropout layer set to 0.25, and a DEDS2 layer with softmax activation and bias initialized to 0. So we trained this for 120 epochs, and the model had approximately 23,000 total trainable parameters. So we show some of our training metrics plotted here, just the loss and the accuracy versus epoch, basically just to demonstrate that our dropout layer did do a sufficient job in preventing overfitting to the training set. So we used 3 different performance metrics in the evaluation of our models. The first was a minimization of the normalized root mean squared error between the ground truth probability of firing in that output neuron and the predicted probability of firing in that output neuron. Second, we use maximization of the correlation coefficient between the ground truth probability as well as the predicted probability. And then lastly, we use the actual recovery of those known 8 neurophysiologically inspired kernels, which were used to generate the synthetic data. So as shown here, our model reduced the normalized root mean squared error between the actual probability of firing in the output neuron in the test set, as well as the predicted probability of firing in the test set to 0.0132. And, we also achieved low error by accurately estimating the true probability of firing on a global and local time scale. And the scale and the plot on the left here is just kind of zoomed in on these signals on kind of a short time scale to kind of show how the predicted probability matches the actual probability. And the plot on the right is just to show that we achieved high correlation between the ground truth probability of firing and the predicted probability with a correlation coefficient of 0.9664 here. So in order to find the recovery of the ground truth kernels used to generate the data, we wrote an impulse response function that took our CNN model and a neuron index as arguments, and we used time series generator again to generate batch inputs into this. So in this impulse response function, the first input would be an image with an impulse with a single one at the argument neuron index at time current within a sparse matrix. And then we create 255 subsequent images for input where the impulse was at increasing time lags for each subsequent image. So we input these images into our trained CNN and generate an intermediate output from predictions from the output from the dropout layer. And then we perform matrix multiplication of that intermediate dropout layer output with the dense layer weights for the spiking class. So as shown in the plots here, of the predicted kernels overlaid on each of those 8 ground truth kernels that we used to generate the initial data, the CNN did a very good job of recovering these ground truth kernels. And this included both on the global time scale that we show here, as well as kind of more locally as we've shown previously. So, we found that our best performing model recovered the ground truth kernels and also had very good performance with minimization of the normalized root mean squared error, as well as maximizing the correlation between the ground truth and predicted probability of spiking in our output neuron. Initially, our first attempts kind of mirrored these best-in-class image classification networks, AlexNet, LayNet, some of these, but we found that they had so many trainable parameters, it was leading to overfitting. So, for our situation, we kind of discovered that using a stride between 1 and alternating between 1 and greater than 1, but less than the filter length in different layers of the CNN provided the best results for us. So in conclusion, we found that a CNN can learn the kernels that you use to generate data in a synthetic generalized functional additive model of spike transformation between layers. And our current work is basically using this same modeling approach to try and model higher order dynamics with second order self and cross kernels, as well as applying our model to animal data. So with that, I thank you all for your time, and I'm happy to answer any questions that you guys have.
Thank you again, Bryan. That was great talk. We have 1 minute if you have a question to post it. Before the question comes up, have you looked at the sensitivity of your model to number of neurons here?
You mean the number of input neurons?
Yes. Yeah.
We have. I mean, we didn't do any type of formal modeling with that. We do know that from our past work that it does scale with the number of neurons pretty well. But no, I mean, just for these initial publications, at least we kept it fixed at 16 for now.
Great, but the architecture is scalable. I see. It doesn't matter the number of neurons, right?
Correct. Well, at least in the, this is synthetic data. So at least in that, obviously as we apply this to animal data, that's going to likely change, but that's kind of yet to be seen for us.
Also, just for curiosity, is that like dropout changing the outcome dramatically? Change the value of the dropout?
Is what changing the value of the dropout?
Yes, yeah. So you had a dropout value in your model, right?
Right.
Yeah. Does it really change the outcome if you change the dropout values?
It did. I mean, we actually, yeah. So it did. Initially we kind of started with a standard dropout of about 0.2, and we did do a hyperparameter search around there. I think anywhere from 0.1 up to as high as 0.5. So yeah, it really did significantly help to prevent overfitting, and also would change the training time as well.
That is very interesting. I usually heard that dropout is not working as well, but that's interesting that you have seen the reverse.
Yeah, it works very well for us, actually better than L1 or L2 regularization here.
That is very interesting. Yeah, I saw that there's another regularization. Thank you so much, Bryan. That was a great talk. And by that, we have to wrap up these sessions. I thank again all the 3 speakers today, and a special thanks for Dr. Sang for having this great PhD students. We are looking forward for your future publication and your scientific impact. Thank you so much again. See you all virtually for the rest of the conference, probably.
Bye.
Thank you.
Bye, everybody.